So last week we got ourselves into a position of understanding the topology on function spaces, the compact open topology, and we proved, I was calling this the adjunction property. It's also sometimes called the exponential law for topological spaces. Since we missed the lecture last week, I'm not going to go through the theorem at the end of, I guess it's lecture 12, which discusses how to identify the space of functions from x to y as a subspace of the space of closed subsets of the Cartesian product, which allows you to think about functions in terms of their graphs, or more interestingly, the topology on functions in terms of neighborhoods of graphs. I think that's interesting and sort of useful conceptually, but okay, so we have to move on. All right, so I discussed at the end of last lecture sort of the ideas leading up to the construction of a metric on function spaces. Well, we now know how to think about that as a topological space for any x and y. So this question makes sense. When is that topology actually induced by a metric? There's an exercise there which asks you to sort of works you through the fact that y sits as a subspace of CTS xy. So certainly if you want CTS xy to be metrizable, y better be metrizable. So that's our starting point. So if we have some metric on y, when can we use that to put a metric on the space of continuous functions? And in the case when x is finite and discrete, I sort of explained how that was reasonable last time. Now we're going to do the general case. Okay. So maybe I'll state the theorem, and then, I need to develop some preliminary stuff first, but it'll be helpful to know where we're going. So here's the theorem. So if x is compact and y is metrizable, let's just say, pick a metric. So y is a metric space. Then there is a metric which will denote d infinity on the space of continuous, well, let's say the set for the moment, the set of continuous functions from x to y, which is defined by just taking the supremum over all the distances between fx and gx, where x is in x. And I'll justify why that's well defined in a minute, although I sketched it last lecture. So that's first claim is that's a metric. And moreover, the associated topology, so the topology induced by that metric d infinity, that's a metric on the functions, well, the set of functions, and it's precisely the compact open topology that we've already discussed. All right, so at least when x is compact, and while y being metrizable is a necessary condition, and it's also sufficient. All right, that's what the theorem says. So notice that this d infinity, maybe I should more precisely say dy comma infinity or something, because it clearly depends on the choice of metric dy. So what we'll see from this as an immediate corollary is that if two metrics on y induce the same topology, then the associated metrics on, so assuming y is compact, on the set of functions also induce the same topology. Right? Because if I chose two metrics, say dy1 and dy2, which determine the same topology on y, well, that's enough to determine the topology on the function space, right? I only need, in the compact open topology, only depends on the topology of x and the topology of y. So if I had two metrics on y inducing the same topology, then the two associated d infinities, where I put dy1 here and respectively dy2, they must give the same topology on the function space. Okay, so that topology is independent to some degree of the metric you choose. All right, so that's the function space as a metric space. So we're going to prove the theorem, but I need to make some definitions first. I forget whether I've mentioned this already, but so if I have a metric space, then the metric, well, it's a map, and big surprise, it's continuous. That's not part of the definition, right? But it's true. So it's continuous where I give y cross y the product topology. I'm going to use that in a minute. I haven't really needed until now the following concepts, so I haven't defined them, but you may have seen them around. That's interior and closure. Okay, so given a topological space and a subset, the closure of the subset, well, it's by definition the smallest closed set which contains A. Well, closed sets are closed under intersections. So if I take every closed set which contains A, form the set of those things, and take the intersection over all those sets. So all the things that are in common to every closed set containing A, that's closed and it contains A, and by construction it's the smallest such thing. So that's the closure. And the interior of A is the union of all the open sets contained in A. Okay, same justification. So it's the largest open set which is fully contained in A. So there's some simple properties of these constructions which I'll ask you to work through as an exercise. So something belongs to the closure if every open neighborhood of X intersects A. So when you see a statement like this, some set intersects A, that more precisely means the intersection of that set with A is non-empty. So every open neighborhood of X has a non-empty intersection with A. Okay, these are just basically immediate consequences of the definition. If I have a metric space, I could ask what is the closure of the open ball around a point. All right, so if I give you a metric space and a point and an epsilon, well, first of all, I could look at all the other points in Y whose distance to little y is less than or equal to epsilon. I claim that's closed. If you like, that's a consequence of this, right? Because what's that set? It's dy blank y. That's a function from y to r. Well, if a function is continuous, its partial functions are continuous, so that's continuous. And I'm taking the pre-image of the set, well, if you like, it's this. Right, I could put up to minus infinity if I like, doesn't make any difference. So the pre-image of that set is exactly what I've written on the right-hand side over there, and the pre-image of a closed set under a continuous map is closed. Okay, so that's closed. I mean, that's maybe not the easiest way to see that. So this, by definition, is contained in this, but it's not necessarily equal, okay? So be a bit careful about that. You might like to find a counterexample. And that's sort of a natural fallacy to imagine that those are equal. This I want to use in a second. So if I have a continuous map, I can ask what is the relationship between the image of the closure and the closure of the image, and that's it. Okay. Well. Okay, hopefully that's obvious. Okay, so that's the closure and the interior. All right, so step one is to check that this is a metric. Well, maybe we should, I guess step 0 is to check that formula even makes sense, right? So maybe let's do that. Okay, well, so suppose given two continuous maps from x to y, f and g. Well, by definition of the product, there's a unique map into the product whose components are f and g. So that's the map x goes to the pair f of x, g of x. Okay. Sorry. Should be y. Hey. Right. So we've got continuous maps f and g from x to y, and then just take the pairing gets us to y cross y, and then I can apply the metric on y. We've just discussed that's a continuous map. And well, this is continuous by the definition of the product. So that's a continuous map. Well, but X is compact. So the image of X under this continuous map is compact and therefore bounded, right? And the image is precisely the set of all dy's of f of x, g of x, where x is in x. Well, so in particular it's bounded above, so the supremum makes sense. So that's a well-defined formula. Right, so notice we use compactness of x in a sort of serious way there, right? Okay, so that's the well-definedness. So step one, let's check that this is a metric. Maybe I won't write down some of the initial steps. I'll do the triangle inequality perhaps, but so let's just discuss out loud the first couple of properties. So what did I call it? So M1 says that the distances are non-negative. Well, the distances in y are all non-negative, and I'm taking a supremum, so certainly those have to be non-negative. Okay, so that's fine. Symmetry. Well, if I interchange f and g here, that interchanges f and g there, but the metric on y is symmetric. Okay, so symmetry of d infinity is also clear. What about d infinity fg being 0? Well, d infinity fg, maybe I'll do that one. So, to say the supremum of a set of non-negative real numbers is 0 is to say they're all 0. But because y is a metric space, I know that's if and only if f of x equals g of x for all x, and that's the definition of two functions being equal. Okay, so that's M2, I guess. Right? Okay, so that only leaves the triangle inequality. So given f, g, and h, okay. Well, we need to show that d infinity fh is less than or equal to d infinity fg plus d infinity gh. Actually, this argument is familiar to you from this extremely laborious question on the first assignment. Right? I mean, if you're trying to prove something about supremums, well, I mean, the left-hand side is a supremum of a bunch of real numbers. To prove the supremum is less than or equal to something, I just have to prove each of the things I'm taking the supremum over is less than or equal to the given thing. Right? So for x and x, we have dy fx hx less than or equal to this. Right, that's by the triangle inequality in y. But that individual thing is less than or equal to the supremum. Well, let's just write d infinity fg. The supremum of all such real numbers over all x is exactly this, so that's less than or equal to that, and similarly that's less than or equal to d infinity gh. Well, then I've proven for every x that this number is less than or equal to that, so that is an upper bound for the set whose supremum is d infinity fg, so by definition of supremum. We have the desired inequality, that thing there. Okay, so that's pretty routine. So that's a metric. Okay. Well, the tricky part is proving that the topology induced by that metric is the same as compact open topology. So step 2. So T d infinity, that's the associated topology, is the compact open topology. All right, so there's two directions. So what we've defined this by a sub-basis, right? These SKUs. And we define this by a basis. Those are the open balls. So I have to prove an inclusion two ways with respect to those open sets. So I guess I'm doing this direction first. So T d infinity. So remember the notation Txy was the compact open topology. Okay, so let's do this direction. So we just have to show that an open ball in this metric is open in the compact open topology. All right, so given an F and an epsilon, so we need to show that B epsilon F is in Txy, and that'll be sufficient because that's a basis. Okay. Well, since F is continuous, F of X is compact. Okay. And hence the following collection of open sets which cover the image as a finite subcover. I mean, proofs involving metrics are always annoying for this reason, right? It's like, well, why epsilon on 3? I don't know yet, right? I have to wait till the end of the proof to find out. It's very irritating. So just sort of, doesn't really matter what that is for the moment as long as they're all the same, okay? So you take some open cover of, so you've got the image sitting inside Y, take an open ball around everything in the image of the same radius. That's all we've done so far. Okay, as it turns out, we need it to be epsilon 3 for the argument to work. Okay, so we covered the image by open balls, and well, that image is compact, so we know we have a finite subset which does the job. And let's call that, say, y1 up to yn. Well, yeah. So all the y's are in the image, so we might as well give names to something whose image they are. Right, so let's call them fx1 up to fxn. Right, we just picked n elements of the image, the open balls around which are a cover, and then we picked images in the pre-image of those elements and called them xi. All right, so okay, what the hell is that, you're thinking? All right. I mean, somehow I need to get myself into a position of showing that this F does the right thing, right? That it sends some compact set into some open set. So I've got to produce a compact thing, right? Now, X is compact, so it's easy to produce a compact subset of X. I just need a closed subset of X, right? Well, that's closed by construction because I took the closure. So that's easy to produce the closed set. I just need to show that it gets sent into something open. Well, that's, you know, that's by construction as well. Right, so this is not as complicated as it looks. Now I need to mess with the radii so that so that the end some triangle inequality works, but that's not so important, right? So the idea is that this is going to get sent into that. Yeah. Okay. So, well, those pre-images are open. I took the closure, so that's a closed set. That's clearly an open subset of Y. And then we just calculate, right? So f of ki, and the calculation just hinges on this observation, just on this, which, you know, give yourself a minute and you'll check that with no difficulty. That's not difficult. All right, so that's f of f inverse of this ball. But that's contained in f of f inverse closure. Well, f of f inverse of something is just okay. I mean, f of f inverse of this is contained in this, and therefore this closure is contained in that closure by property, the last one down there. Okay. And well, here you see why I took the epsilon on 2, because I want this ball to be contained in the open ball, so I can't take epsilon on 3, but I just need to take something a bit bigger, right? So whatever, take epsilon on 4 and epsilon on 5, who cares, right? Just needs to be small. So that's contained in b epsilon on 2 fxi, okay, which is ui. Right? Because if something's distance to fxi is less than or equal to epsilon on 3, well, it's certainly strictly less than epsilon on 2. That's all that's saying. Well, so we're done. Okay, so f is contained in ski ui. Well, Therefore, f is contained in the intersection. And those intersections are part of the topology. Okay, so at least I picked an f and I got it lying in some open set. I mean, that's not such a big deal. That doesn't complete the proof. I need to show that actually this epsilon ball is fully contained in that open set, right? So that around f there's something open. Well, I think I said that around the wrong way, didn't I? So let me explain, since I managed to confuse myself. What are we trying to do? We're trying to show that that epsilon ball around f is in the compact open topology. So what I'm going to do is show that that intersection is contained in the open ball. And that's enough then to show that that open ball is contained in the compact open topology, that it's open. Okay, so let's prove this inclusion. So suppose I mean, maybe that doesn't quite seem sufficient, because it seems like I've just found an open neighborhood of a single point in B epsilon f. But if you think about it, since I did it for any f, it actually does show that the topology associated to the metric is contained in the other topology. Okay, so suppose this is in there. So we need to show that it's within epsilon of f. Well, that means that the supremums of all these things have to be less than epsilon. And what do we know? We know that gki is contained in ui for each I. So we need to show that this is true. Yeah. Why 5 epsilon on 6? Yeah, well, you'll see. Okay, so what we're going to do is so we took a g in this intersection. We're going to show this is true for all x, which means this supremum is less than or equal to that. And then we're going to use that to show that g lies in that epsilon ball around f in the metric. Okay. Right, because then the supremum of all those is less than or equal to epsilon on 2, and therefore less than epsilon. Okay, so then g is in the epsilon ball around f. Okay, well, so far we haven't used, so now we use the fact that we actually had a cover, right, of the image. So since the Okay, so we're proving this inequality for each x in x. Okay, well, there's some I such that f of x lies in that open set because those things cover the image, and that's in the image. All right. Well, for that to be true is precisely to say that dy of f of xi is less than epsilon on 3. And hence that x is in ki, right? Because what's the definition of ki? Well, it's the closure of something, and it's the closure of precisely the things that satisfy that condition, right? That their image lies in the epsilon on 3 ball around fxi. Okay. Well, if x is in ki, then by definition, since g is in these intersections, it sends x to something which is in ui. So g of x is in ui. But ui is the epsilon and 2 ball around fxi. So we have by the triangle inequality dy gx fx is less than or equal to, so use this particular I. Right, so gx being in ui says that that first thing is less than epsilon on 2. And then the second thing is, sorry, that's fx, right? Going from gx to fx. And that thing is from here. Right? The distance from fxi to fx is less than epsilon on 3. Okay, so hence this business with the 5 epsilon on 6. All right, so that succeeds in proving that, and then that implies this. So G is in the epsilon ball, and that completes the proof that everything which is open in the metric topology is open in the compact open topology. Right, so now we've got to prove the reverse inclusion. We have to show that SKU is open in the metric topology for K in X, well, compact, which is the same as to say closed, and U in Y open. Okay, so this is a little tricky. So I'm going to invoke some auxiliary results, which I'll prove afterwards. So we're keeping this hanging, and let me state the auxiliary results. So those of you who did the exercise earlier about minimizing the distance to a compact set, that there's an element which realizes that as a consequence of the extreme value theorem, that's the idea we need to invoke now. So what are we going to do? So we're supposing, let me just set it up a little bit more, perhaps. So if F is in SKU, so FK is contained in U, and well, FK is compact. All right, so let me state the result we need. This is lemma L13-4. So it says that if we have a metric space, a compact subset, and an open subset, third time's the charm. Okay, the compact set is contained in the open set. I mean, that's the situation we have here, right? So my f of k is the thing that's playing the role of k over there. So I've got a compact set contained in an open set. And there exists an epsilon such that for all k in k and x not in u, we have dyxk greater than epsilon. And it sort of makes sense if you think about the picture. It's not, takes a little bit of thought to prove, perhaps. So what's the picture? It's that here's my compact set. I've sat it inside an open set. That's a disappointing green. There's an open set, and there's X. All right, think about, so you fixed X, which is outside of K, and it's bounded away from K by some open neighborhood. And you look at the distances from X to every element of K. And it's saying that there's some minimum to that. That's exactly the same as to say the infimum is non-zero, the infimum of all those distances, right? Okay, so it sort of makes sense, I suppose, if you think about it. We'll prove it in a second, but we're just going to use it now. Okay, so we've got our compact set that's contained in our open set, and the lemma provides us with an epsilon. What letter am I going to use for the element that's not in there? Say y. All right, so I took my compact set, I took the image, it's contained in this open set. For everything outside the open set, which we're calling y, the distance to anything in the image, which is our compact set, which is things of the form f of k, is greater than epsilon. Okay, so what we claim is that the epsilon ball around f is contained in SKU. So that's an open neighborhood of F in the metric topology, so that will be sufficient to prove this. Why is that? Well, if G was another thing which was within this distance of F with respect to the sup metric, well, then that would have to be true, right? Because this by definition says that the supremum over all x in x of that distance, dy fx gx, is less than epsilon. So in particular, it's true if I take just those points in k. Okay. But you can see how this forces some condition on the gk's, right? Right, so hence gk is in U. Right, because if gk was not in U, then gk would be one of these y's, and we know that those distances are greater than epsilon, which is not true. So we know that gk must be in U. Well, so that means that G sends k into U, which is what we needed to show. Okay, so G is indeed in that open set of the compact open topology. Okay, so that proves that inclusion, and so we're done. All right, so the sup metric on the set of functions, continuous functions, just recovers the compact open topology in this case. So I want to prove this now. Are there any questions about the main theorem first? Yeah.
Number 13.4.
Yep.
Says if what K in Y compacts, can K and U open with K and U again?
Yeah, thanks. Yeah. So. Yeah, thank you. Was this what I had before I erased it? Yeah, all right. Because I looked, I thought I was looking at this one. I'm like, why did I write that? Okay, yes, thank you. So I've got a compact set contained in an open set etc., etc. Okay, yeah, thanks. Any other questions / corrections? Okay. All right, so well, before I give the proof for the lemma, I need to prove another fact. This doesn't continue forever, I promise. Yeah, then I'll get to the end of the lecture and be like, okay, I'm out of time. So I hope that doesn't happen. All right. That's right. Yeah. Okay, so this hinges on the following fact, and this proof. So, well, in a metric space, we know how to measure the distance between points, right? But we can sort of make a reasonable definition of the distance from a point to a set, which is just take the infimum over all the distances of things to points in the set. Right? So let y dy be a metric space, and A and y a subset. Then we just define the distance from y to A. It's just the infimum of all the distances from y to arbitrary elements of the set A. Okay, so I mean that's bounded below because they're non-negative, so that certainly makes sense. I mean, it's not guaranteed at the moment that that has any good properties, but I claim that it does. I mean, if you start thinking about how to prove that, what you immediately want to use is this, basically, right? Which is that that function is continuous in y. I mean, that makes sense, right? Because here's y, there's my set A, and here's my y. So you can imagine I take the closest point in A. That's not quite accurate, right? It's not guaranteed that that distance is realized by anything. But you can kind of think of that as the distance I'm talking about. And as I move y around smoothly, you would imagine that the distance also moves around continuously. Yeah?
So are we assuming that y is not in A, or is this in A?
Oh, you're right. Yeah, y could be in A for this definition, in which case it would be 0. That's correct. So if and only if this is 0. Yeah. Yeah.
Wouldn't it be 0 if like it had an adherent point which wasn't an interceptor?
Oh, you're right. I didn't say it was close. Correct. Yeah, that's right. Yeah. Yeah, exactly. So it would be 0 if and only if it was an adherent point. Yeah. Okay. So why is that continuous? All right. Well, okay, so if I pick 2 points in y and anything in A, well, the distance from x to capital A is certainly less than or equal to the distance from x to that individual A, by definition. And then by the triangle inequality, I can split that up into this. Okay, so what that means is that dxa minus dxy is less than or equal to dya. And that's less than or equal to, sorry. Well, what I had there was true, but it wasn't what I need. So let me put it back in for a second. I'm going to get rid of it again. I mean, that's true. That's a consequence of just rearranging this, right? But the left-hand side doesn't involve A. That's the point. So this quantity, which depends only on x, the set, and y, is less than or equal to this for every A, and therefore it is less than or equal to the infimum over all A, which is exactly what I get if I replace little a, the specific A, by capital A. Right? So that is less than or equal to the infimum of all of them, which is dy A. And this is basically, I'm done now, right? So that means dxa minus dya is less than or equal to dxy. So this is, this forces it to be continuous, right? If you like. So that means the absolute value is less. To get this, just observe that the right-hand side is symmetric in x and y. So if I swap x and y on the left-hand side, which is multiplication by a negative, I get the same inequality. So that follows from that. And therefore, continuity says I'm allowed to make this small in order to make that small, which is clear if that inequality holds. So therefore, this function is continuous, as claimed. Okay, so now quickly, let's go back to the lemma. Now this is basically instantaneous. Well, so what's the function I want to talk about? It's this unwieldy looking thing. Okay, take the complement of u, that's closed. Take this function, so that's the thing that measures the distance of things, so what's it, y? Measures the distance of things to the complement of u. That's continuous by the lemma, and therefore it's continuous if I restrict it to k. Well, now we use the extreme value theorem. Right? K is compact. So I've got a continuous function on a compact set. The extreme values theorem says that its infimum and supremum of its image are realized. That is, there's an element such that evaluating that function on the element gives you the infimum of the image of that continuous function. Right? So by the extreme value theorem, there is a k in k, let's call it k0, such that applying that function to that particular element gives you the infimum of all these elements. And I'm trying to bound this thing below, but I've basically succeeded now, right? Because x is in U complement. So I just take that to be half the distance from that minimum element to, U complement. And that's positive. Right, well, why is that? Well, dkx, if I take x not in U, dkx is one of the things I'm taking the infimum over. So dkx is greater than or equal to that, which is greater than half of that. So this epsilon works, and that epsilon doesn't involve x at all, right? So it works for every x. And for that, I just needed to know that the infimum here was realized by something. Why did I need to know it was realized by something? In order to show it's not zero, right? I could write down this infimum. I can do that without any of this trickery with the continuity. But then how do I know that's not zero? Well, I know it's not zero because it's forced to be actually realized by something, and that distance from k0 to the complement can't be zero because k is not in the complement, right? So I know this is non-zero because this thing is in k, and I know I can do that with an element of k by the extreme value theorem. So that's how that all fits together. All right, so That allows us to prove that, allows us to finish the proof of that. And that's me out of time.